Hello, my name is Ankan Roy Bardhan, and today I am going to present my topic for the course Image Processing and Computer Vision for 2013. My course project is Correlation Coefficient Maximization in Image Alignment Problem using Image Registration. Now you see there's two important key terms, image alignment and image registration, play a vital role in our project. We will see how this works. Now we'll go through the outline of the project. We'll first go through the definition of image registration technique. We will understand what is image registration. Secondly, we have certain geometric transformations which transform one image to another sort of image. The same image which is transformed to another type of image, and we would try to implement image registration technique to get back the original image from the transformed image. We will come up with two terms called objective function and the parameter estimation. The objective function is nothing but a function which is depending on the reference image and the transformed image, which is also called warped image, and we will try to minimize the difference, and somehow these images transformation is depending on a parameter, and if we have the parameters we can use the bilinear transformation to get back the original image from the warped image. The algorithm which has been put forth is called the forward addition iteration algorithm, and this algorithm is typically very important to get the parameters, and then if we get the parameters we can backward warp the transform image. And finally we'll go through the MATLAB project codes, and we'll see the complexity and convergence time of these iterative algorithms. Now, what is image registration? Image registration is a process of transforming different sets of data into one coordinate system. For example, if you have a template image and a transformed image, we can somehow see that there is a mapping of every point in the template image to the transformed image. This mapping is called the image registration. Now this is fairly useful because if you take a snapshot, a photograph of a single object from different light exposure, from different camera angles, these photographs could be different to a computer, but to a human eye it could be the same. To a computer it is different because of the fact that if the computer tries to deduct one image from the another image, it doesn't get the zero. That means there is some kind of mismatch. We try to reduce this mismatch as much as possible and fuse them into one image so that the content of the image is rich, the information is rich. Image registration is widely used in medical imaging, for example PET or CT scan. Now I'll show you what image registration technique actually does. For example, if you have an image like this, I'm showing you only the region of interest, a square region, and suppose this image has been rotated with some angle, say theta, to this image. This image is called the reference image, this is called the warped image. Now what the image registration tells is there is a mapping between every point in the reference image to every point in the warped image because it is basically the same image. This is a mapping. This point maps to this point maps to this point, and this point maps to this point. Not only these 4 points, but every other point should map to one specific point in the warped image. This is basically image registration. Now this all mapping depends on a parameter P. If we somehow find this parameter, we can backward warp this image to get back the reference image. Now, as I said, we have 4 sorts of geometric transformation. These are translation, Euclidean, homography, or affine. What are the transformations will be shown in the subsequent slide, or you can refer to the project report. Now these transformations are basically disaligning the original input image, and our objective is to use the image alignment image registration technique to get back the original image. Now as I said, we would only consider the region of interest. This is important because if we consider the entire image and the iteration for every point, it would take a huge amount of resources in terms of CPU, time and power. So we will consider only a specific region of interest, which could be a square section or triangular section or anything. The region of interest is only deformed, and that is only backward warped to obtain the original image. This backward warping is only possible by estimating the parameters, as I said in the previous slide. And this algorithm is termed as forward addition. Now, you see, as I said, the four types of transformations which has been used. The red box is only the region where we will use the image registration to get back the original image. So this, if you see, this box is not exactly a rectangular, it is slightly deformed. This transformation is called affine transformation. Similarly, this transformation is called Euclidean transformation, which looks something like a rotation. This is basically a translation, which is nothing but just taking a small subsection of the image which is very parallel to the original image, and this is homography, which is a combination of other transformations. Now another important thing to note, the parameters should be different, or the approach should be different for each type of transformation. We will see in the code how. Now the mathematical modeling. The mathematical modeling says the reference image is termed as IRXY or IRX bold, and the warped image is termed as IRX-Y dash or IWX bold dash. Now the point is, say X dash is the point in the warped image and X is the point in the reference image. This is exactly the mapping which is happening. We don't know phi exactly because we don't know p. If we know it, we can use bilinear transformation to get back this X reference image. Now in the theory, or in the report that has been developed with this project, contains a objective function which is defined as MP of this form. This is calculated solely by deducting the reference image with the warped image and minimizing the difference. By minimizing the difference, we would get this term to be maximized so as to get the minimization of the difference. In the theory, gradient method has been used and the Jacobian plays an important role. Now the iteration is fairly simple. If you have, suppose if you have arrived at a step j minus 1, which is pretty close to the jth step, which is supposed to be the optimum. So we have a set of parameters, pre-calculated parameters, and if it is added with a small amount of pj, it arrives at the optimal value. So this is forward addition. You forward add the small p delta pj to the previously optimized p to get the new p. So this delta p in the theory has been deduced. This is defined as this term. G is basically the gradient, and this small I and small iw is basically relates to this IR and IW. The reason is, if you take a snapshot of an image from different light exposures, the intensity values will be different. So it is very tough to correlate one image with another image. This is called the photometric deformation. Now our algorithm, we try to remove this photometric algorithm whatsoever, because photometric transformation should be there always. So we have to devise an algorithm which is less susceptible or non-susceptible to any sorts of photometric distortion. So what we do is, we deduct the intensity vector of the reference and the W warped, we divide or we normalize it with the norm of this vector. So by maximizing this objective function, we get this maximizing is nothing but just taking the differential with respect to p. Now if we get the delta p as this one, which depends on lambda. Lambda can be any three of these, which is basically has been deduced in details in the theory or in the project report, you can see. And finally the backward warped. If we get the delta p from the previous image or the previous iteration, we add it to the previously optimized value, we get the new warped image vector. Now image registration technique compares 2 points from both the images and is used for analysis. Now it is, as I said, it is used in medical imaging, like seeing the visibility of tumor in MRI scan. Image mosaicing, where pieces of a single image could be joined together by using image registration, and a single photograph is constituted from all these parts. Same goes for motion and pattern detection. You have different images, different frames of a moving object. You can correlate these all frames to have a optimized flow, to have a constant flow of the object, so that it looks like a motion. And finally the topic of our project, which is basically image alignment and reconstruction of the warped image. Now we will go through the MATLAB demonstration in the next video.